We'll start in 1 minute. We'll start reviewing for the final exam today. We'll also spend Monday and Tuesday of next week reviewing for the final. Okay, the final exam is scheduled for Wednesday, December 2nd, from 7:30 a.m. to 9:30 a.m. Mountain Standard Time. And the final exam will be proctored in the same way that the other tests were proctored. You could use a paper sheet of handwritten notes on the front and on the back, and the dimensions should be no more than 8.5 inches by 11 inches. So I would advise start working on that sheet of notes now. You might want to revise it between now and when you take the final. And some things that you can do to prepare for the final: review the problems on tests 1, 2, 3, and 4, and review the test review sheets. The final exam will have problems that involve Taylor series, Maclaurin series, and Taylor polynomials, and some test review sheet style problems from those sections 11:10 and 11:11 will follow. So let's get right into it. Find the sum of the power series. The terms are n to the second times x to the n from n equals 0 to infinity. So what this means is find the function whose power series is this power series. So a hint on trying to find the function. Well, we know what this power series is. So this one is 1 plus x squared and so on. This one is 1 over 1 minus x, right? For values of x between -1 and 1. But what if I took the derivative of each of the terms and wrote n times x to the n minus 1? So if I took the derivatives of those, I would get n times x to the n minus 1. And then if I multiply every term by x, I would get the series that looks like n times x to the n. And then if I take the derivative again, I get a sum n to the second times x to the n minus 1. And then multiply every term by x again, I would get the series that I want. Do you follow that? So we're going to begin with this series where the terms are x to the n. We'll take the derivative of the function 1 over 1 minus x to get this one. Then we'll multiply every term of that by x to get this series. Then we'll take the derivative of that to get this series, and then we'll multiply every term by x again. Sounds tedious. Okay, so 1 over 1 minus x is 1 plus x squared, and so on. Whoops, x to the n. Duh. And then we take the derivative. What's the derivative of 1 over 1 minus x?
1 over 1 minus x squared.
Yeah, this one is 1 over 1 minus x quantity squared. And this is 1 plus 2x plus 3x squared, and so on. So this one is, I'll squeeze it in there. So let's see, let's start at 1. N times x to the n minus 1. Okay, then multiply every term in this series by x, so we get x over 1 minus x quantity squared. And this will be x plus 2x squared plus 3x to the third, and so on. So this will be n times x to the n. Okay, so in the next step, we'll take the derivative of x over 1 minus x squared. So just use the quotient rule for the derivative. The derivative of x is 1. We multiply that by 1 minus x quantity squared. And then we subtract x times the derivative of the denominator, which is 2 times 1 minus x to the first, and then multiplied by -1. And then divide this by 1 minus x squared squared, which is 1 minus x to the fourth. And one factor of 1 minus x will cancel from all of the terms. So in the numerator on the left, we'll still have one factor of 1 minus x. This factor, 1 minus x, is gone, and so we have minus x times 2 times -1, which is going to turn out to be plus 2x. And the denominator is 1 minus x to the third, because one factor of 1 minus x canceled. Okay, so we get 1 plus x over 1 minus x quantity to the third. So this is the derivative of this series up here. So I'll rewrite 1 plus x over 1 minus x to the third. And then the derivative of each of those is 1 plus 4x plus 9x to the second plus 16x to the third, and so on. So this one written as a sum. So this one will start at 1, and it's n to the second times x to the n minus 1. Okay, then the next step is the last step. We just multiply this function by x. So when we multiply the left-hand side by x, the numerator is x plus x squared divided by 1 minus x to the third. Multiply all of these terms by x. We get x plus 4x to the second plus 9x to the third plus 16x to the fourth, and so on. And here we can start at n equals 1, and this is n to the second times x to the n. Well, my original one starts at 0, but that's okay because when n is 0, the first term up there is 0. So the non-zero terms start with n equals 1. So the answer is this function over here on the left, this rational function. Hey, let's do the next page. So we can go through these pretty quickly. We know that e to the x is 1 plus x squared over 2 factorial, and so on. And so Maclaurin series for e to the x squared, all we have to do is replace every x in the series for e to the x with x to the second. So we get 1 plus, replace that with x to the second, and then x to the second is x to the fourth over 2 factorial. And then the next one, x to the sixth over 3 factorial, and so on. So in sigma notation, we get x to the 2n over n factorial. All right, the next one, how should we start finding the Maclaurin series for 1 minus cosine of x over x squared? Yeah, we'll write 1 minus, and then the Maclaurin series for cosine of x. So cosine of x, the Maclaurin series is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, and so on. then we're dividing this all by x to the second. So when we have 1 minus this, 1 minus 1 is 0, and then we change the signs of the other ones. So we'll get x to the second over 2 factorial minus x to the fourth over 4 factorial plus x to the sixth over 6 factorial, and so on. We're dividing this all by x to the second. So divide each of those by x to the second, we'll get 1 over 2 factorial minus x to the second over 4 factorial plus x to the fourth over 6 factorial, and so on, minus x to the sixth over 8 factorial. So let's try to get it into sigma notation. So we know it's alternating. So where should we start n? We can start it any way we want. Sometimes it's easier starting it at one number or another. Let's just start out with 0, so -1 to the n. And the numerators will be x to the 2n, and the denominators 2n plus 2 factorial. I think that will work. When n is 0, we get x to the 0, which is 1, over 2 factorial. Yeah, that looks like that one works. Okay, what about the next one? F of x equals 3 over 3 minus x. Well, the way I would start this one, I'll factor 3 over 3 out. And so we get 1 in the numerator, and in the denominator, 1 minus x thirds. And 3 over 3 is 1. And then 1 over 1 minus x over 3, that's just going to be 1 plus x over 3 to the first plus x over 3 to the second, and so on. So we can just write the sum from n equals 0 to infinity of x to the n over 3 to the n. So if you multiply those out a little bit, we get 1 plus x over 3 plus x squared over 3 squared, or 9, plus x to the third over 27, and so on. Okay, the next one. So this one looks a little different than what we've seen, but we know how to do it. We can bring all of the components of our understanding to work on this one. We know what the series for arctangent is. So up here, I'll just write arctangent of t. So if you don't remember this one, you can figure it out pretty fast. But it's this one is t minus t to the third over 3 plus t to the fifth over 5, so on. Is that how you remember? Okay, then if we, the integrand is arctangent of t divided by t. So we can just write down what we get when we divide each of those terms by t. So it's the definite integral from 0 to x of 1 minus t to the second over 3 plus t to the fourth over 5, and so on. Okay, then in the next step, we just write antiderivatives for each of those terms. We're going to evaluate the integral from 0 to x. Okay, so antiderivatives. Antiderivative of 1 is t, and then minus t to the third over 3 times 3. I'll just write 3 to the second. And then plus, what's the antiderivative of t to the fourth over 5?
T to the fifth over 5 squared.
Yeah, t to the fifth over 5 squared. And it follows the same pattern, antiderivative of t to the sixth over 7, t to the seventh over 7 to the second, so on. Then evaluate this from t equals 0 to t equals x. Well, when t is 0, all of the terms are zeros, so let's just replace every term with every t with x. We get x minus x to the third over 3 squared plus x to the fifth over 5 squared. So you know the pattern, so let's write it in sigma notation. So let's start with n equals n equals 0, I guess. So it's alternating, so -1 to the n. And the x terms will be x to the 2n plus 1 divided by 2n plus 1 quantity squared. Okay, so that wasn't so bad. All right, let's move on to the next page. This is a variation of the problem that we didn't get to on Wednesday. We'll find the third degree Taylor polynomial of the function f at a equals 1, and the function is f of x equals x to the 2/3. And then after that, we'll use that degree 3 Taylor polynomial to estimate f of 1.1. Okay, so we need the function and the first 3 derivatives. So f of 1 is 1. So the first derivative, or function is x to the 2/3. So the first derivative is 2/3 times x to the negative 1/3. And then evaluate this at a equals 1, we get 2/3. Then the second derivative is 2/3 times negative 1/3 times x to the negative 4/3. Evaluate the second derivative at a equals 1, we get negative 2/9. So I'll use some of this space up here. We just need one more derivative. The third derivative is 2/3 times negative 1/3 times negative 4/3 times x to the negative 7/3. And then we evaluate the third derivative at a equals 1. This time we get positive 8/27. Okay, so just as a reminder, the coefficients of this particular Taylor polynomial will be the nth derivative of f evaluated at 1 divided by n factorial. So we can start writing down what the third degree, or the degree 3 Taylor polynomial is, t sub 3 of x. So the first one, 1 over 0 factorial is 1. And then plus 2/3 over 1 factorial times x minus 1 to the first. Then the second derivative evaluated at 1 is negative 2/9. So we'll write minus 2/9 divided by 2 factorial times x minus 1 squared. And then the third derivative evaluated at 1 is 8/27. So plus 8/27 divided by 3 factorial times x minus 1 to the third. So let's just do a little bit more work on this. 1 plus 2/3 times x minus 1. And then minus 2/9 divided by 2 factorial is minus 1/9. And then times x minus 1 squared. And then the next one, we will get 8/27 divided by 6 simplifies to 4 over 81. 4 over 81 times x minus 1 to the third. Okay, so this degree 3 Taylor polynomial is approximately equal to f of x. So f of 1.1, which is 1.1 to the 2/3. That's approximately equal to the Taylor polynomial evaluated at 1.1. So let's just fill in some of the details. 1 plus, and then 1.1 minus 1 is 0.1. So we have 1 plus 2/3 times 0.1. And then minus 1 over 9 times 1.1 minus 1 to the second. So what's 1.1 minus 1 to the second simplify to? 0.01. So 0.1 squared is just 0.01, right? And then the last term plus 4 over 81. And 1.1 minus 1 is 0.1, and 0.1 to the third is 0.001. So the numbers on the right side, as if you were to increase the degree of the Taylor polynomials, the numbers on the right side are pretty small after a while. So it looks like the Taylor polynomials approximate the function pretty quickly in terms of the size of the degree. So that's all we'll do on that one. But just one note, it looks quite a lot easier to do the arithmetic on using the Taylor polynomial than to raise 1.1 to the 2/3. So that is one of the, evidently one of the reasons Taylor polynomials are used is because they are just evaluating polynomials. Okay, let's start reviewing the Chapter 7 material. So make sure that you know the integration by parts formula for integrals. So if you have an indefinite integral of the form u times dv, then that's equal to u times v minus the indefinite integral of v times du. So for this one, the integral of 2x times e to the 3x, well, usually if we can, we pick u to be the function that can be made simpler by taking the derivative. So I would pick u to be 2x and dv to be e to the 3x dx. And then du, that's the derivative of 2x, which is 2, and then dx. And v is an antiderivative of e to the 3x, which is 1/3 times e to the 3x. And then using the formula, u times v, 2x times 1/3 times e to the 3x, we'll write it as 2/3 x times e to the 3x. And then we subtract the integral of v to u. So it's the integral of 1/3 times e to the 3x times 2 dx. So we can write it as minus the integral of 2/3 times e to the 3x. And we still have one more antiderivative to find. And be careful with the signs. So we're going to subtract the indefinite integral of 2/3 e to the 3x, which is 2/3 times 1/3 times e to the 3x. So I'll just write it as minus 2/9 times e to the 3x, and then plus a constant. So make sure you practice the integration by parts. This is just a fairly simple example. Then in section 7.2, that's the section on trigonometric integrals. And a lot of time could be spent reviewing trigonometric integrals. We're not going to have the time to review every single thing. So review as many of those as you can. Try to remember the basic derivative and antiderivative formulas for trigonometric functions and some of the basic identities. So here are just some examples that involve some useful identities. To find the indefinite integral of sine of 2x dx. Is there anything that comes to mind that you could do?
Half angle identity?
Do what?
Half angle identity?
Yeah, the particular identity that I'm thinking of here, sine of 2x is equal to 2 times sine of x times cosine of x. So in my opinion, this isn't the only way to do it, but in my opinion, this works really nicely. So replace sine of 2x with 2 times sine of x cosine of x dx. And then to proceed, is there something that comes to mind when you look at the indefinite integral of 2 times sine of x cosine of x dx? The thing that jumps out at me is an application of the substitution rule. So if I pick u to be sine of x, du is cosine of x dx. So when I substitute, I get the indefinite integral of 2u du. And then what's the antiderivative of 2u?
U squared?
Yeah, u to the second plus a constant. And then we put back what u is, so we get sine of x squared plus a constant. Are we in agreement? Okay. The next one, another pretty common identity for cosine of x squared.
That would be 1/2 times the quantity of 1 plus cosine of 2x.
Yeah. Cosine of x squared is 1/2 times the quantity 1 plus cosine of 2x. So we'll bring the factor 1/2 out to the front. So we have the indefinite integral of 1 plus cosine of 2x. So we'll get 1/2, and then an antiderivative of 1 is x, and an antiderivative of cosine of 2x is plus 1/2 times sine of 2x. Plus a constant. So this is a pretty good answer. If you want to distribute multiplication by 1/2, you can. But for now, that's good enough. And then related, or in a similar vein, a common identity for sine of x squared is, at least when computing antiderivatives, this one is 1/2 times the quantity 1 minus cosine of 2x. In a different setting, we might use a different identity, but just computing an antiderivative of sine of x squared, this is probably maybe the best one to pick. So let's see, the next step, 1/2 times x, and then minus 1/2 times sine of 2x plus a constant. Okay, the next one, the indefinite integral of tangent of x to the 5th times secant of x to the second dx. Anything come to mind on this one?
The antiderivative of secant squared is tangent.
Yeah, secant of x squared is the derivative of tangent of x. So using u substitution, a lot of these trigonometric integrals, there's more than one way to do it. But the thing that I notice is if I pick u to be tangent of x, then du is secant of x squared dx. So when I make substitutions, I get u to the fifth times du. And then an antiderivative of u to the fifth with respect to u is u to the sixth over 6 plus constant. And then replace u with tangent of x again. So we get tangent of x to the sixth divided by 6 plus a constant. So there are no doubt other ways to do that. Okay, let's go on to the next page. Trigonometric substitutions. There are essentially 3 of those trigonometric substitutions that hopefully you'll recognize when you see them. So on this one, we have the indefinite integral of 1 over a to the second plus x to the second dx. So on this one, the denominator a to the second plus x to the second. So this has the form where I decide to pick x to be a times tangent of theta, or some other variable if you don't like theta. Just don't pick x. And so x to the second is a to the second times tangent of theta squared. We do need to know what dx is. So dx is a times secant of theta squared d theta. And why did we pick x to be a times tangent of theta? I guess we have room all to say a squared plus x squared is a to the second plus a to the second times tangent of theta squared, which is a to the second times 1 plus tangent of theta squared. But 1 plus tangent of theta squared? Yeah, secant of theta squared, so we get a squared times secant of theta squared. Okay, so that's what a to the second plus x to the second is. So replace dx with a times secant of theta squared d theta. I'll go ahead and put it all in the numerator, a times secant of theta squared d theta. And then the denominator is, we are replacing a to the second plus x to the second with a to the second times secant of theta squared. A over a to the second is 1 over a. It's just a constant. Secant of theta squared divided by secant of theta squared is 1, so we get 1 d theta. And then we evaluate this, we get theta divided by a plus a constant. Okay, and what is theta?
Arctangent of x over a.
Yeah, since we defined x to be a times tangent of theta, that means x over a equals tangent of theta. And so theta is the inverse tangent of x over a. Okay, so the answer to our problem is 1 over a, we still have that constant, times the inverse tangent of x over a plus a constant. Okay, for the next one, we have the indefinite integral of the square root of a squared minus x squared dx. So which trig substitution should we use this time? So I'll do half of it. X equals something. You do the other half.
A sine of theta.
Yeah, sine of theta. Or, sorry, a times. Yeah, you said a times sine of theta. A times sine of theta. So dx is a times cosine of theta d theta. And let's do a little more arithmetic. The a squared minus x squared is a squared minus a squared times sine of theta squared. Factor a to the second out, we get a to the second times the quantity 1 minus sine of theta squared. But 1 minus sine of theta squared is cosine of theta squared. Okay, so we'll put in all of that stuff. We're going to get the square root. Instead of a squared minus x squared, it's the square root of a squared times cosine of theta squared. Dx is a times cosine of theta d theta. The square root of a squared times cosine of theta squared is a times cosine of theta, and then times a times cosine of theta. So a times a is a to the second. That's a constant that we can bring out front. And then we have cosine of theta squared for the integrand. And we saw that already today once. We should take it a little bit further because our integral has to be expressed in terms of x. So replace cosine of theta squared with 1/2 plus 1/2 times cosine of 2 theta. So if we bring the factor 1/2 out front, multiply a to the second times 1/2, we get a to the second over 2. And then the integral of 1 plus cosine of 2 theta. Theta. So we'll probably run out of room, but the antiderivative is theta plus 1/2 sine of 2 theta plus a constant. Okay, so we need to find theta, but that's based upon our assignment. X equals a times sine of theta. So x over a is equal to sine of theta. And theta is inverse sine of x over a. So we're going to replace theta with that. And what are we going to do with 1/2 times sine of 2 theta? Since we're running out of time, I'll just use the space down here, and then on Monday I'll give you final exam review part 2, including that problem maybe. So 1/2 sine of 2 theta is 1/2 times 2 sine theta cosine theta, or just sine of theta times cosine of theta. And we're using this. This will help. We know what sine of theta is. Sine of theta is x over a. And then cosine of theta, well, let's see. If theta has a sine that's equal to x over a, then this adjacent side is the square root of a squared minus x squared. And so cosine of theta is the square root of a squared minus x squared over a. So we're out of time. This got a little sloppy. So on Monday, I'll just write this up a little bit more nicely and show you the finished work when we start on Monday. But that's all we have time for today. Yep.